All right, rapid fire 5 coming your way. Graphical and algebraic, solving some log equations and doing some inequalities. Going to start with the graphical and algebraic. It's new to you as to even what I'm asking. So I'll start with an absolute value equation. Let's go with 2 absolute value of x minus 3 plus 4. And let's set that equal to 50. All right, so graphical. Graphical is not actually solution, it's approximations. We just want to get a sense of when we do the algebra, do the answers make sense? So there's 2 graphs. Graph 1 is the left side of the equation. Graph 2 is the right side. We want to put those graphs, not necessary to actually graph an XY axis for these. In fact, I would encourage you for most of them not to do that. So this graph is a V-shaped graph. We're looking at 3, 4 as the vertex, and that's a height of 4. And if I put a 0 in, I get 10. 0, 10, I'll put here. And we want a height of 50, which is actually up here somewhere. And I'm looking for that x value and that x. And so we have a 0 here, and we have a 3 here, and I'm way out here somewhere. And I'm over here somewhere, and I'm looking for that x. We'll call that x1, and over here x2. Let's do x1 over here, x2 over here. Smaller to bigger. And we're estimating. So I know that's 6 units, and I got to go up. Well, I got to do that another 4 or 5, 6 or 7 times. Real quick, 7 times 6, 42. So 7, that's a change of 3 from 0 to 3. So 7 times 3, 21 units in that direction. This should be near negative 20. And then this one over here, 21, and I forget. So let's just say from 3, 20. Let's just say we're at 25, maybe, something like that. These are real rough estimates, right? So if I get answers when I do this that are in that vicinity, I got a feeling I didn't make a mistake. That's all I want you to do with graphical, is to get a little, I was going to say snapshot, but I think given the, that's kind of telling my age, I think we'll call it a screenshot. All right, so how do we solve this equation? Well, we've been practicing that in class. 2x minus, cup shape up, so minus 2, x minus 3 plus 4 is one of the branches, and I want that to equal 50. And over here, positive 2, x minus 3 plus 4 equals 50. Remember, you're pausing the video on these things, right? You're trying this stuff, and if it doesn't immediately come to you, then just watch what I do. That's the first step of learning, is following. So I'm just going to do this quick. I'm going to do all of these quick because, it takes some time. So I'm going to subtract 4, 46, divide by negative 2, negative 23, add 3, negative 20. You know what? That was a pretty darn good guess. I didn't put as much time into this one. This one, subtract 4, 46, divide by 2, 23, and add 3, 26. I thought I was off by 1. I had 26 because it was 3, but I didn't spend enough time thinking about it. All right, so that's problem 1. I'm going to do 5 of these. Do something we did not do in class. And I'd like you to see it, so I'll do it, and that way you can get a little practice with that. So let's do an exponential. Let's do a 12e to the x minus 4 plus 5, and let's make that equal to 9. All right, so we're going to graph this side, exponential growth. That's a height of 5. My first jump is going to be 12. My next jump is going to be 36. That takes me to a height of, should put a comma here, 17. If I pick the right number, I think the right number is 4. Let's check it. 4 minus 4 is 0. E to the 0 is 1 times 12 is 12 plus 5. Yes, it's 17. And I've got an x value of what makes a 0, 4. Well, actually, that's enough for me right now, because I know I'm trying to hit a height of 9. Well, a height of 9 is over here somewhere, right? It's, 1/3 of that. So my answer should be, well, I guess I got to see how much I'm jumping by here. I think I want to use 5.11. 5, 5.1. That's what I want, I think. 5.1 minus 4 is 1.1. I know what e to the 1.1 is. It's approximately 3. That's why I did 36. 3 times 12 is 36. And 5 is 41. So this is a height of 41, and that comes from 5.1. Okay, so I changed by 1.1 to go that way to triple. I want a height of 4. I think I want to go 5.1 this way. I think I'm going to be at 4 minus 5, negative 1.1. I think I want negative 1.1. My brain's a little tired right now doing that in my head. All right, so a height of 9 is a constant. There's your screenshot, and we're looking for that x value. I'm saying I think it's near this, might be exactly that. No, I know it's not now. I think I wanted looking at it. I think I wanted, well, let's just do it out because the brain is tired. So I'm subtracting 5, which makes that 4. I'm dividing that by 12, which makes that 1/3. I'm doing the inverse of e, which is the ln of 1/3, which is the negative of the ln of 3. So that is approximately negative 1.1. And then I am adding 4 to that. And that's what I had trouble with a minute ago. So negative 3. Yeah, that was pretty bad. So negative 3, so negative 2.9. So if I put negative 2.9 in here, minus, so just 2.9. Yeah, the brain is tired, isn't it? Positive 2.9. So 2 minus 9 is negative 1.1. E to the negative 1.1 is approximately a third. A third of 12 is 4, plus 5 is 9. Okay, so I did talk eventually about what should have happened. All right, you'll have to forgive me. I'm doing math here for the last 8 hours, and I'm starting to get a little fatigued in terms of my computational skills. But it's good to tire the brain out like that once in a while. Just like going to the weight room, tire those muscles out, they come back stronger the next time. So what's another one? Another one could have been something like x minus 2. I think I did this one. X minus 10, something like that. And let's let that equal to negative 21. So I did the right thing here. 3, no, negative 15. So then 3, yeah, that works pretty good. All right, so this, you haven't really practiced graphing that all that much, which is why I'm putting it in front of you. I'm hoping you see the major operation is squaring, and that's cup shape up. And what does this tell me? That tells me my roots are at 2 and 10. And if I put a 0 in, I get 20. So that is now 20 units high. I think that's something akin to what I'm graphing here. And I want negative 15. Sometimes you don't have to find the vertex, but I think you do this time. That's 2 gets me a 0, and over here 10 gets me a 0, right? And what's the number between 2 and 10? 6. So I'm going to put a 6 in here, and that gets me 4 times negative 4, which is negative 24. So I know negative 15 is about there. There's your screenshot. I want to know that x value. I know it's between 2 and 6. It's probably 4 or 3, something like that. So, and I want to know something between 6 and 10 over here. You know, so something between 6 and 10, 7 or 8, maybe 9, something like that. All right, so we do it out. How do we do it out? Well, we multiply that and we get x squared minus 12x plus 20. We want that to equal negative 15. I could put it in graphing form and do inverse operations, but it's always good to set it to 0 first, just to see if you can factor. I don't know if it's always good, but yeah, 12, 35, 5 and 7 is nice. X minus 5, x minus 7. So one of my answers is 7. Yep, that's in the estimated range. And the other answer is 5, and 5 is between 2 and 6. So over here, you know, I could do a better graph with more time, but trying to just get the idea here. So if I put a 5 in here, I get negative 15. Doesn't hurt to try it. So 5 minus 2 is 3. 5 minus 10 is -5. And what's 3 times -5? -15. So that one works, that one works. And that's the third one of rapid fire 5. Of course, oh, good, I got a eraser here. I was gonna say, I don't have one, but obviously I've been erasing as we've been going along, so brain is really tired. So what's another type of function that is worth doing? Well, these are ones you haven't seen yet, but you're gonna. So square root of x minus 2 equals x minus 2. Do it graphically first. We're gonna graph y equals the square root of x minus 2. Well, I know some square roots. I know the square root of 4, the square root of 9, the square root of 16, etc. Right? So if I make x minus 2 any of those numbers, I can plot. First off, of course, is knowing the shape of the square root, knowing what creates the endpoint, which is 2. A square root is a distance, right? What's the smallest? This area is really x minus 2. That's what I do. You take a square root of an area. And so what makes this area 0? 2. And that's what's going on conceptually. This one, I think I want to actually put on an XY axis. So that's 2. We'll make that a distance of 2. So this is 0, 0. We just found out 2 gets you 0. I like the square root of 25. I just like it. So square root of 25, I don't in this case. If that's 2, maybe I'll go to 9. Because I want to get a good little estimate. So a 9 gets you 3. Square root of 9 gets you, oh, I got to pick 11. I told your brain's tired. 11 minus 2 makes the square root of 9. There, now we're up and running. Right? And I am going to graph x minus 2, which is linear. That's a linear graph. That's the y-intercept. It's also the x-intercept. So this thing is, I picked a nasty one for you. I'm sorry. Didn't mean to do that. All right. Yeah. So this thing actually has 2 answers. A lot of times they only have 1. That's actually going to have 2 answers. One of them is going to be 2. And the other is going to be something between 2 and 11. I don't know, 4 or 5, somewhere in there. Looks to be pretty accurate graph here, I think. So how do we solve this? Now, you pause the video and give it a couple of minutes. Nah, I think I give it 10 to 20 seconds of thought. And if it doesn't come to you, then we'll just acknowledge that my brain is really tired. All right, so square both sides. Now there's a problem with squaring both sides. So here's an equation, x equals 3. If I square both sides, I get x squared equals 9. And if I solve that, I get x equals plus or minus 3. Well, the original problem only had 1 answer. So you got to be careful when you square, because you might get what's called an extraneous root. And we've got to make ourselves sound important here. Extraneous root. Extra answer. All right, so we're squaring that, right? So x minus 2 equals, we've been squaring binomials, x squared minus 4x plus 4. Move everything to the other side because it's nice to get areas equaling 0 so you can factor. X squared minus 5x plus 2. No, don't tell. Oh, plus 6. Well, there's only one way to get a negative in the middle and a positive at the end, and that's an x minus times an x minus. And it looks like it's going to be 2 and 3. Yeah, and I said one of our answers would be around 4 or 5. Turns out it was 3. That's where that intersection is. Probably should have seen that more clearly before, but as I said, I'm losing it. So x is 2 and x equals 3 is how you solve that one. That's good enough, I think, for graphical and algebraic. We'll do one log, because you're really trying to dissipate the fog on logarithms. So we'll do a log, because I don't remember graphing a log today in class. And I want you to get little looks at everything as much as possible. It'd be great if by the end of the semester we could take one of those tests and finish it in half an hour. Boy, that would be good if you really know it. So let's just give a basic log here, and I'll show you how I do these. So let's do log base 2. Let's just do x minus 4 plus 7. Okay, so what's a log base 2 that's friendly? I think 8 is friendly. Okay, so what makes this 8? Well, My answer to this equation is going to be 12. So I put 12 in, I get that. 3 times 3 is 9, plus 7 is 16. That just shows you there's no magic in my making these things. So what's a logarithm look like? Well, this is a log, which is the inverse of growth. So it's going to look like this. We always want to set our parentheses to 0. So that tells me x equals 4 is the border. I need numbers bigger than 4 because these parentheses represent quantities. You got to have some. It's got to be a petri dish. It's got to be a radioactivity. So that has to be positive, which means we have to be bigger than 0. All of these places are bigger than 0 for x. Then we want to set x minus 4 to 1 because I don't care what the base is. Doesn't matter what this base is. That's 0. Right? You put a 0 on top of something to get a 1. So I'm going to pick the number 5. We'll put 5 right there. Let's make this thing continue down forever. And a 5 makes the log 0 times 3 is 0. You'll always get that. And then if we make this a 2 and that a 2, then that's a 1. Real easy to multiply something times 1. So what makes this 2? The number 6. So 4, 5, 6 would be here. And then that gives me 1 times 3 is 3 plus 7 is 10. If you make that 1, you do that, set the parentheses to the base, you'll always get that. And I think 3 times 0 is the best multiplication and 3 times 1 is the next best. And that's what we're doing. Now, where's the height of 16? 7, 10, 13, 16. 16 is about here, right? And this is slow growth. And so it looks to be 5, 6. Well, we knew the answer was 12. And not the best graph, but not bad. So now the question is, how do we solve this? Well, let me clean this up. So the only thing you're doing now is seeing the algebra. So I hope you're starting to get the feeling for it. Here's the major command. We're going to get rid of addition, subtract 7. We're going to divide by 3. Okay, and that isolates the major operation. We have to undo the major operation, which is using the base and the exponent to get the quantity. So x minus 4 is equal to 2 cubed. That's 8. 4 plus 8, there's your 12. So we did an absolute value, we did a quadratic, we did a square root, we did an exponential. I might have said that twice for all I know. And we just did a log. There's 5. Okay, now we're going to do the inequalities. Did I do? Okay, inequalities. So let's do 2x times x minus 3 times x minus 4. Okay, so let's make this x minus 10. All right, and we want to be greater than 0. I'm going to graph that for you later up here. It's easier to do this graphically, but you're learning the sign chart at the moment. So what are the roots? 0, 3, and 10. And these are all to the first power, so we're going to get sign changes all over the place. I'm going to put a number bigger than 10, a million times a million times a million. That's bigger than 0, so this is true. This will be false. This will be true. This will be false. But you can check it. So we're going to get sign changes. So I picked 10. When I picked 10, I got a positive, positive, positive product bigger than 0. When I pick 9, I get a sign change. 10 or 9 doesn't matter here. 10 or 9 doesn't matter here. It doesn't affect those parentheses. But now the product is negative, and a negative product is false. It's not bigger than 0. But we're going to get another sign change when I pick a number between 0 and 3. Let's pick 2. Oh, when I put a 2 there, that changes. When I put a 2 here, that's still negative. It doesn't affect that one. When I put a 2 there, that's positive. All right, what's that product? Negative times a negative? Yeah, that's true. That's true. And you'll find that if you put a negative million in here, and a negative million in here, and a negative million in here, everything is negative. And a negative times a negative times a negative is a negative, and a negative is not bigger than 0. So, interval notation, 0 to 3, union, 10 to infinity. Now, if I know that this thing, when I use a 10, is positive, polynomials head to infinity. Squaring heads to infinity quicker than next to the 1, and cubing, well, that's squaring, right? But the end behavior is always going up. So if I found out this polynomial is going to positive infinity, then all I had to do was put an xy axis. I got roots at 0, 3, and 10, and I'm going up, coming down, going up because of the sign changes, positive to negative, the positive to negative. I'm looking at the y values. Y values above the x-axis positive, below negative. That would have been a quicker way of doing this problem. And I'll be showing you that, but right now I'm only holding you accountable for just making a sign chart. So let's do another one. Let's do 5x squared times x minus 3 times x plus 4 to the third. Let's be, I forget what I did the last time, less than 0. Less than or equal to 0. All right, so that's even. So I like to put a little dot there because I'm either going to get something that looks like that or looks like that at this instant. It takes on the quadratic look to it, just briefly. And I don't know which of those it's going to be yet until I find out the end behavior. So, no sign change at 0, sign change at 3, sign change, this is to the 1, odd, get a sign change. I like to use a dash to indicate that. All right, and God, I only get 40 minutes on these recordings. Okay, I hope I'm just talking fast here, but you pause the video. Put a number bigger than 3 in. Positive, positive, positive. False. Okay, so that's false. Changes signs there. True. Doesn't change signs at 0. Changes signs at 3, yes. Doesn't change signs, does change signs at -4. Right? So what's the or equal to? Well, it looks like it's from -4 to 3 is working. So I would show it this way. Less than or equal to 3, greater than or equal to -4. I think that's better than interval notation when it's just one interval. All right, no need for interval notation then. Now, what would the graph have looked like? I would have done the same thing there. I would have said, okay, dot at 0, sign change at 3, sign change at -4. We know when we put bigger numbers than 3 in, we're going to positive infinity. So it would have looked like this. Right? And where are we less than or equal to? Yes, well, not here. Right? That interval. All these x's don't work. These do, because they kick out things that are less than 0. 0 works. These do, but all these x's, they kick out things bigger than 0. So that's how you would have looked at it graphically. And that's like a double parabola. 2 and 1 make 3. So you're looking at an x to the 4th kind of polynomial. But not, probably the symmetry is way off. But we're just trying to get the x's that work. All right, so let me try another one. And it doesn't have to be a product. It could be a division, x minus 3 over x plus 4, greater than 0. What are critical numbers? Well, that's to the 1. That's to the 1. So I get sign changes at 3, and I get sign changes at -4. So I just try some numbers. I'll put 1,000,000 in. 1,000,000 divided by 1,000,000. That's true. It's greater than 0. Not a very big number. So if I get sign change, false and true. Now the graphs. I'm not even going to show you that graph right now because those are going to take a while. I might show you a few, and then I'm going to check Algebra 1 curriculums around the country and see if it's something that I can hold you accountable for or not. But these are a little tricky, so I'm not going to show you the graph. I really should, but I won't. So where am I at? So true, interval notation, negative infinity. Can't bracket negative infinity. I also want, I didn't say or equal to, I'm going to go or equal to, because I want you to know something about that here. So let's put -4 in. -4 plus 4 is division by 0. You can't divide by 0, and I wanted you to hear that. You can divide something into 0. So this number will work. All right, so what is the interval notation? Negative infinity, -4 doesn't work, so negative infinity, can't bracket it, to -4, yeah, you can see that, and that number does not work. Union, but 3 does work, so we give that a bracket, and that goes to infinity. All right, I'm not gonna do 5 here, because I think I might only have 40 minutes on Zoom. I don't know how long we've been doing this. So that gives you a little practice, and you'll get some more on Monday. I'm gonna do a couple of logs here. So let's say we have log base 2 of x and log base 2 of x minus 2 equals 3. Okay, so these are all exponents. When do you add exponents? When you have a number to an exponent, right? That's when you add exponents. What does it come from? Multiplication. Multiplication of what? The quantities. So I'll write this now as a single quantity situation. So I'm multiplying that times that. That equals 3. You're trying to rewrite that so it makes more sense to you. Here's a problem that I hope makes more sense to you. Log base 5 of 25 equals 2. We can see 5 squared equals 25. So we apply what we see here to this problem now. So 2 to the 3 equals x squared minus 2x. We set these to 0, so I take the 8 and move it to this side, and then we hope we can factor it. And we can. 0 equals x minus 4 times x plus 2. -2 and 4 are my candidates. I can't put -2 in here. You have to log positive numbers. So this one doesn't work. Let's see if 4 does work. Now you're just learning this, so let's look at it. What's the exponent you put on top of a 2 to get a 4? A 2. Let's put a 4 in here. 4 minus 2 is 2. What's the exponent you put on top of a 2 to get a 2? A 1. 2 plus 1, by God, equals 3. Okay, so that's how you do a problem like that. Try another one. All right, let's try log base 2 of x minus 4 plus log base 2 of x plus 5. Let's set that equal to 3. I have no idea if we're going to even get a solution here. I'm going to make this minus, excuse me. Sorry if you already paused the video. All right, so if addition was multiplication, intuitively, I hope you realize that subtraction is division. So as a single logarithm, I could have written that. Now, how do we solve that? 2 to the 3 is 8. Right, so I can move this 2 to the other side and put it there. And now I have x minus 4 over x plus 5. Division by x plus 5 becomes multiplication by x plus 5. I've got 8x on this side. I'll subtract x and make it 7x. I've got positive 40 on this side, which makes it negative 44 on this side. I can't do this. Negative 44 minus 4. There's no solution to this problem. Sorry, I made something up that didn't really work, but still had us talk about some things that are important. So let me see if I can find something that is a little easier to do with a subtraction. So let's look at log base 2 of x minus log base 2 of, God, I'm probably not going to get integer answers here. Log base 2 of 4. I don't want that. Yeah, maybe I do want that. Equals 1, just to show you the mechanics of this work. All right, so subtraction becomes what? Subtraction becomes division. It's probably a good idea I do it this way. Okay, you rewrite it in exponential form. Exponential form means there's got to be a base. Oh yeah, it's base 2. So x over 4 equals 2 to the 1. So it looks like x equals 8. So we'll put an 8 in and see if it works. What's the exponent you put on top of a 2 to get an 8? A 3. Minus, what do you put on top of a 2 to get a 4? A 2. And 3 minus 2 does equal 1. So hopefully you can trust that. I'll do one more. Got to come in under 40 minutes here. Otherwise, I've just done this and I'll have to do it again. I think I'll lose my mind. So let's do log base 2 of, yeah, let's do x minus 1 plus log base 2 of, God, do I have any prayer of getting something right here? 17, 16. So if I make this 17 and I subtract 9, please be right. Yes, 3 and 4, that's 7. Okay, so this should be an integer answer. All right, so what do we got? We got log base 2 of multiply x squared minus 10x plus 9 equals 7. Okay, not too bad. So x squared minus 10x plus 9 equals 2 to the 7. And 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. 64, 128. So I think this number is 128. So I'm going to subtract 128. I get x squared minus 10x minus 119 equals 0. So what numbers are 10 apart that multiply out to be 119? 17 and 7. So this is x minus 17 times x minus 7 equals 0. Can I use 7? No. 7 minus 9 is negative 2. Nice try, Jim. Can I use 17? 17 minus 1 is 16. What do you put on top of the 2 to get a 16? A 4. 7 minus 9 is 8. What do you put on top of the 2 to get an 8? A 3. And 4 plus 3 is 7. All right, I'm sorry, it's mixed up all over the place there, but play it several times. All right, gave you a little bit of practice. All right, might not have been rapid fire for each one, but Zoom now is only giving us 40 minutes because we're not Zooming a whole class. So I'm going to stop this real quick so I don't lose things. Oh God, I hope it's under 40.